Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Devi Classes YouTube channel where we inculcate interest and confidence in science and engineering subject. Today in our playlist Basic Electrical Engineering and Class 12th Physics in our chapter Alternating Current Circuits, we'll study the behavior of pure resistance in alternating current supply, and we'll soon found that in an resistance circuit, when alternating voltage is applied, an alternating current of same phase will result, and in those conditions there would be always flow of electric current produce heat energy, and power is though fluctuating but always positive. That means electrical energy always get converted into heat energy. So let's understand the behavior of pure resistance in alternating current circuit. Resistance shown by these zigzag line in circuit model is property of electric circuit which oppose flow of current in it, and for current flow this resistance demand proportional voltage. Now such resistance R is connected across a standard reference sinusoidal alternating voltage, and supply voltage is trigonometrically instantaneous magnitude is given as Vm sin omega t. Here Vm is maximum value of sinusoidal time varying alternating current or amplitude of oscillating voltage, and this omega is angular frequency of supply voltage. Now the resistance characteristic opposition to the current flow will act in an identical manner in both alternating current supply and direct current supply, and its behavior remains the same irrespective of the frequency of alternating current supply. When the alternating current change its direction after every half cycle, the drift motion of electron also change, but the collision among drift moving electron convert electrical energy into heat, and again the opposition of circuit component remain as it is. So we can say change of magnitude of alternating current or direction of alternating current doesn't affect the resistance behavior, and we can say in a resistance, if physical condition of conduction remains the same, the instantaneous current flowing through the resistance is directly proportional to the instantaneous voltage applied across it. As per Ohm's law, the instantaneous current flowing through the resistance and voltage which is applied across resistance both are proportional to each other, and this proportional relation can be converted into equality, and this equality constant is property of circuit which oppose flow of current in it and demand proportional voltage for circulation of current, and this property is called as resistance. And in pure resistive circuit we can say instantaneous current is instantaneous voltage divided by resistance, and since current and voltage are proportional to each other, so if we make voltage n times, the current will also become n times. So there exists a proportional relation between applied voltage across resistance and current flowing through the resistance, and if our voltage is standard reference sinusoidal alternating voltage denoted as Vm sin omega t, then current through resistance is V by R, and this expression can be simplified as Vm by R as amplitude of current and sin omega t, and this Vm by R in front of this sinusoidal function is Im, or amplitude of sinusoidal alternating current flowing through the resistance, or maximum magnitude of current. So we can say in a resistance the peak magnitude of alternating current flowing through the resistance is equal to peak voltage applied across resistance divided by resistance property, and in terms of RMS value, if we divide both sides by root 2, then Im by root 2 become RMS current, and RMS current I is given as Vm by root 2 divided by R, and Vm by root 2 is Vrs, and if RMS voltage is V, then RMS current is V by R. This expression is just like a DC expression, and in place of DC average value we can apply RMS AC values, and I is V by R, or V is equal to IR. We found that voltage across resistor and current flowing through resistance are proportional to each other, and when alternating sinusoidal voltage is applied across resistance as shown by this orange waveform, the current passing through it is also a sinusoidal alternating current of same frequency and same phase. It means both voltage and current achieve their positive peak at the same time instant. Both increasing in positive direction have half of peak magnitude at the same time instant, and both have zero instantaneous value, and voltage change its polarity, current change its direction at the same time instant. So both have zero phase difference, or both are in the same phase. So we can say in a resistance, when alternating voltage is applied across it, alternating current will result in the same phase with alternating voltage, as shown here in orange waveform alternating voltage and in cyan waveform alternating current. So orange alternating waveform of supply voltage across resistance and cyan waveform of current through resistance are as shown here, and these curves clearly indicate that both voltage and current have their positive peak or negative peak or zero cross at the same time instant. So current through resistor and voltage applied across it, both are in the same phase, and all through this variation similar type of phase condition, say half of positive peak in decreasing condition, occur at the same time. So same phase conditions of current and voltage in resistance occur at the same time instant. When sinusoidal alternating voltage is applied across resistance, this supply voltage alters its polarity after every half cycle, and at that very instant when voltage is altering its polarity, the direction of current flow also get altered. So the change of sign of voltage and current take place at the same time instant. With one polarity of voltage, current flow is always in one direction, and as the polarity of supply voltage changes, at that very instant the direction of current flow in resistance also get changed. So we can say in a resistance circuit, the alteration of sign or change of polarity of voltage and change of direction of current takes place simultaneously, because one change is the result of other change. The graphical presentation of phase relationship between alternating sinusoidal voltage wave and alternating sinusoidal current wave is also represented by phasor diagram, and since supply voltage across resistor is standard reference voltage with phase angle 0, then its phasor is plotted at horizontal reference line, making 0 phase difference from horizontal reference, and since current of resistance is in phase with voltage applied across it, so current phasor is also in phase with voltage phasor, both get aligned, and since both applied voltage and flowing current through resistance are of the same frequency, so both phasor will rotate in anti-clockwise direction with same angular velocity corresponds to angular frequency of voltage and current, and after a certain time interval. So both current phasor and voltage phasor rotate in anti-clockwise direction with same angular frequency or angular velocity, and when both travel by 30 degree, both will have in positive direction half of their amplitude value, and when they rotate by 90 degree, both will attain their respective positive peak. So both phasor during rotation remains in the same phase as illustrated in this wave diagram or in this phasor diagram. Since both voltage across resistance and current flowing through resistance got same frequency and same phase, then their respective phasor, current phasor and voltage phasor, always remain aligned with each other all during their rotation, and different position of rotating phasor will have different projected component on vertical axis or different value of instantaneous magnitude, but both instantaneous magnitude remain always in phase. So these rotating phasor always remain in phase with each other during their rotation, and in frozen state when rotation is ceased, the relative position of voltage and current in the same alignment would be the phasor diagram for pure resistance, voltage and current. The current phasor and voltage phasor in pure resistance are in the same phase, and their scale length corresponds to the magnitude of alternating current and voltage, but the relative length of two phasor are arbitrary because current in ampere and voltage in volts represent different quantities, and they can be represented by a proportional length as per the scale used for current representation and scale used for voltage representation. Voltage is defined as amount of work done for circulation of 1 unit positive charge in circuit, and if Q amount of charge is circulated with V potential, the total amount of work done is given as product of voltage and charge. And time rate of work done per unit time is known as power in electric circuit, and it become voltage multiplied by time rate of charge flow, and time rate of charge flow is current. So we can say instantaneous power in a resistance is product of instantaneous voltage across resistance and instantaneous current through resistance. And we know that voltage with peak amplitude Vm is a standard reference sinusoidal wave Vm sin omega t, and current in the same phase with amplitude Im is Im sin omega t. So product of instantaneous voltage and instantaneous current becomes Vm Im sin square omega t, and by trigonometric simplification we can write sin square omega t as 1 minus cos 2 omega t by 2, which represent that this instantaneous power got two factors. One is Vm Im by 2, which won't change with time, is a constant power. This constant power is also called as average power. And the second is a double frequency cosinusoidal variation with amplitude Vm Im by 2. Now Vm by root 2 is called as Vrms, Im by root 2 is called as Irms. So this constant term is product of RMS voltage and RMS current, and this product of RMS voltage and RMS current is also average power. And the second factor is double frequency cosinusoidal function with amplitude, product of RMS voltage and RMS current. We can graphically plot instantaneous power relation as a constant term and a double frequency cosinusoidal function. So time variation of sinusoidal alternating voltage produce in phase time variation sinusoidal current flowing through the resistance, and the product of instantaneous voltage and instantaneous current is instantaneous power as shown by this black wave. And as simultaneously both voltage by change of polarity and current by change of direction alter their sign, the product of instantaneous voltage and instantaneous current again become positive, and power though variable but remain always in one direction, as current whether it is flowing in one direction or another direction. In both case, collision among drift moving electron generate heat, or electrical energy get converted into heat energy, and rate of energy converting into heat is known as power, and power is fluctuating but in one direction only. When the magnitude of current is small, power magnitude is also small, and when current got or attain peak magnitude, power also attain peak magnitude. And this double frequency variation of power have a non-zero average value as product of RMS voltage and RMS current, and a double frequency cosinusoidal variation. So we can say this black dark wave can be consist of two component. One is a uniform constant component, average power, and second is a double frequency cosinusoidal function if we treat 0 here. So the average value of power in resistance for alternating voltage supply or alternating current flow becomes this product of RMS voltage and RMS current. So in resistance connected to alternating current supply, average power is product of RMS voltage and RMS current, and if we apply Ohm's law, V is equal to IR, then this product of RMS voltage and RMS current become RMS current square multiplied by resistance, or if we replace current as voltage divided by resistance, then this average power product of RMS voltage and RMS current become RMS voltage square divided by resistance. And these relation of average power in resistance for alternating current circuit is the same as power relation in DC circuit for a resistance. As in DC circuit, power in a resistance is product of average voltage and average current, or is equal to I square R, or is equal to V square over R. So the power relation in case of resistance in DC circuit and in AC circuit got the same format. The only difference is that in DC circuit these are average voltage and average current, whereas in AC circuit they are RMS voltage and RMS current. So only averaging value get replaced by RMS values, and relation of power remains the same for resistive circuit in both DC supply circuits and AC supply circuits. So a AC supply circuit having pure resistive characteristic can be analyzed just like analysis of a DC circuit. So this simple learning video has explained the behavior of pure resistance in alternating current supply, and now you understand that in pure resistive circuit, alternating supply voltage and current flowing through resistance are in the same phase and their power relations are just like DC circuit relation. The only difference is in place of DC average value, we have to consider RMS value in AC supplies. Our other learning video are equally useful and you can use them in your studies or refer them to your friends. And if you need exam centric notes or online doubt clearing classes, do join our YouTube membership. Happy learning. Have a nice time. Thank you very much.